We'll get started. Welcome to the second session of this online workshop. We are very pleased to have four invited talks, and we'll start with Laura Greene. So without further ado, Laura, whenever you're ready.
Thank you, Chimao. I want to thank you for inviting me and Penching and also for doing these workshops. I think they're terrific. And I was at a workshop this year, and my student who's here, Irfan Mohammed, who's first author on this, has also been to school workshops. So it's planar tunneling spectroscopy of our well-loved heavy fermion superconductor serum cobalt indium 5, investigation of local moment pairing. And so just without further ado, of course, this never works. Okay, so I'm going to sort of set the stage by a complicated outline. So if I don't get through it, you can reach out to me. So one of the things I like to get across is we've all been studying unconventional superconductivity since the 70s, at least I'm old enough to be. And in the old days, we defined an unconventional superconductor in that the order parameter symmetry breaks the symmetry of the underlying lattice. After the iron-based superconductors came out, where the ordered parameter symmetry is the same as S plus minus, mimics that of the underlying lattice, we came to, well, at least I did, came to the conclusion is that this electronic or quasi-powder, whatever the conducting fluid is, above Tc, it what breaks the symmetry of the underlying lattice. And I just basically mean it's a non-Fermi liquid. It's a non-Fermi liquid that the transport optical and thermodynamic properties aren't just determined by how the carriers sit in the lattice. So I'll start with a quick motivation why we study serum cobalt indium 5. I think most of you are better experts than I am. It's a great superconductor. Because of a lot of the people with Joe Thomson, you learn to grow very, very clean materials with a very long mean free path. We showed a few years ago, and it's been agreement ever since then. It's dx squared minus y squared pairing symmetry. But I remind you that pairing symmetry doesn't give you pairing mechanism and vice versa. So there's still a discussion of what the pairing mechanism is. This particular talk will focus on planar tunneling spectroscopy, where we've been able to, with people like Irfan and Keshaf Sharistra, who I mentioned there, have been able to make very reproducible junctions at the three major crystallographic orientations. Lots of polishing, I'll just buzz through that, over low temperature range. And we've looked at magnetic fields up to 18 Tesla here at the Magnet Lab. So what I'm stressing in this talk is that above Tc, about twice Tc, Tc is 2.3, we see a very interesting structure. And it turns out that we get a field-induced splitting or some field-induced gap that only occurs above Tc, but below twice times Tc. So there's like a magic area in there. And I'll kind of point out, and I don't have the hard theory yet, that results are consistent with Cooper pairing is due to Kondo scattering. And then I'll go through summary questions and conclusions. Now, I added something there, but I lost it. Oh, it's in the next slide. I just want to remind you, we have many, many families of unconventional superconductors. And what I'm trying to stress here is that it's the fact that you have all this non-Fermi liquid area above Tc that's consistent with almost all the heavy fermions. I think maybe UP2, that's not true, but nothing is ever 100%. So we have many, many families of unconventional superconductors that aren't plotted here. And I want to bring out is I never expected that if phonons alone can't account for cuprate superconductivity, I never expected there would ever be one mechanism to describe all unconventional and conventional superconductors. So that's always been my premise, and it's very rich. I think you're very familiar with the heavy fermion nature of the transport and the heat capacity, and it's about 85 times the free electron mass in serum cobalt indium 5, and the heavy electrons form the Cooper pairs. I want to point out that this is where you start getting at about 45 degrees T star is where you start getting the real strong hybridization, and you all know this, between the conduction electron and the F levels. And then you get this strong drop in the resistivity, and Tc is down here at 2.3 degrees. So this is the condo lattice effect, and TC is down here. We use point contact spectroscopy to show us dx squared minus y squared. It's been accepted, and this is a very rich slide with a bunch of references in it, which is that there's a bunch of STM out there that agrees that it's dx squared minus y squared, and they also describe either a pseudo gap and or preformed pairs. Basically, all these references here are really interesting, and there's devil in the details, but they all know something funny is going on above TC, and it's not easy to identify. I said that we think we have preformed pairs. A recent publication, PRL 2023, using pressure-dependent point contact spectroscopy with my old student on in Tucson Park on it, they showed that indeed there is a pseudo gap due to condo hybridization, which I think they're completely correct on that. But I think the bottom line is, like the cuprate, cerium cobalt-endium 5 has a rich pseudo gap structure. So above TC, you're certainly going to see the hybridization in the transport. But within that pseudo gap area, our data are consistent with the possibility of preformed pairs. You all know planar tunneling spectroscopy, and just to remind you, and I like to remind people on this, is this here's just aluminum lead, and these little bumps here, these are the phonons. So one of the things we have in this material is that in any tunneling, these bumps in this aluminum lead are lead phonons. That was the indication that phonons were the pairing mechanism. So just to remind you, in tunneling, if you feel what the pairing mechanism is, if it's something you pick up an inelastic neutron scattering or whatever, you have to at some point see it in the tunneling. If you don't see it in the tunneling, it's probably not due to the pairing. And that's one of the things that we want to bring out here. This is just to remind you that planar tunneling, due to Harrison's theorem, I won't have time to go in it, specifically picks up non-Fermi liquid behavior. And again, this is a short talk, so I'm going to go on to some of the meat in this. I'd be happy to discuss this anytime with anyone. But there are many advantages to planar tunneling over STM. One is that I know how to do it, but also that this Harrison's theorem doesn't apply to STM. To remind you, some of you have been to this talk before, we do a lot of polishing and etching. In this case, we plasma oxidize the surface to make the barrier. So if you focus on right here, we have the highly polished cerium cobalt-endium 5, in this case, an aluminum oxide plasma oxidized barrier and a counter electrode of lead. One of the reasons we use counter electrodes of lead or a known superconductor is because we don't understand what's going on, whether it's a cuprate, a heavy fermion, or some interesting material. And if we use a counter electrode of a material we do understand, we could look at the quality of the lead tunneling conductance to have a gauge on the quality of the junction to see if we're really getting single-step elastic tunneling. After we do enough of this work, we get a feel for what the cerium cobalt-endium 5 tunneling conductance looks like, and then we can switch counter electrodes because we have such a good idea what the tunneling density of states looks like in cerium cobalt-endium 5. That becomes no less a diagnostic as to the quality of the junction. And then whether you're looking at high TC or this stuff, you put a little temperature on it, you put a little field on it, you drive the counter electrode normal, and then you're looking at the counter cerium cobalt-endium 5. So this is just to show you the quality of the junction. So the last one I show you was aluminum lead. This one is cerium cobalt-endium 5 lead. And what we have here is the lead. This is really great looking tunneling. But I can't tell you what percent, predominantly single-step elastic tunneling. We're getting a great tunneling density of states. We can see the delta 1 plus delta 2 of the lead of the cerium cobalt-endium 5. Cerium cobalt-endium 5 has a very high HC2, so you put a little field on it and you drive the lead normal, which gives you a cerium cobalt-endium 5 insulating normal junction with very little perturbation to get there. So from now on, I'm going to show you all the junctions will either be with only about 2 kilogauss, just a little over enough to drive the lead normal. And so here's an example here of the 001 or C-axis tunneling. So the lead is driven normal here. So we are only seeing the gap of the serum cobalt indium 5. And here's the 001 direction, the 100 direction, and the 110 direction. I'm going to back up about this 110 direction. When we first started seeing these data, we assumed originally that this peak here was the famed zero bias conductance peak due to the order parameter sign change. We are having trouble fitting that because it's just too broad. So there's something more going on here in this nodal direction than just an Andreev bound state. Here's the detail of the Blonder-Teagham-Clapwick fit, and we have good tunnel junctions. Okay, temperature dependence. So the color plots there are really a guide to the eye. So what we have in the right side, we have 001, 100, and 110 tunneling into those faces. And the dotted line, the white dotted line, okay, I'm sorry, the y-axis in each of these cases is the temperature. And all you really need to know, that of course these colors have to do with conductance, is that above TC, we see stuff going on. If you remember a conventional superconductor like lead, like niobium-3 tin, above TC, you're a weakly correlated Fermi liquid, and below TC, you've got a gap. Here, we know we're unconventional because we have stuff that's non-Fermi liquid that we pick up in our planar tunneling that happens above the gap. And I will point out that you see sometimes a little higher, sometimes a little lower. You can explain all that with Fano effects between the F level and the conduction electron. But in any case, we see a precursor. Now we're going to get to the fun stuff. Now we're going to go down to low temperature and just look at this as a function of field. And, when we started looking for interesting states, this grabbed us and we just started looking at this magnetic evolution. So here's our representative data. Yes, it is our best data. So here we have the 00 C-axis direction. Okay, we're sitting down in 0.4 milli-K, and HC2 in that direction is about 5 Tesla. So here we are, just enough field to drive the lead normal. So we have here the serum cobalt indium 5, the black is the tunneling density states. I'm not using the laser pointer because I can't keep track of it. Okay, now what we're doing here is we're slowly going up in field in Tesla, 1, 3, 4, 6. 6 Tesla is here. Okay, we see this structure that's slowly changing and broadening. I remind you, 6 Tesla is above HC2. There is no superconductivity in these upper figures. There's something going on that's splitting or growing or whatever it is with increased field. We also see that in the 100 direction and the A-axis direction. And so here we have the serum cobalt indium 5 at low field, just enough to drive the lead normal. We go up. Remember, we're above HC2, above 11, 14, 18. Now, again, I said that I can't really explain this entire shape of the 110 material, but we can show you that we get the splitting. We get some kind of splitting with zero applied field. And I mean with the 0.2 Tesla. And the argument for that is that you've already broken all the Cooper pairs at that 110 interface. So you don't have to, break the Cooper pairs that, at that interface because that interface is normal due to the sign change of the order parameter. Okay, so we've seen all this before. Now, the stuff grayed out are the same plots that I had showed you before. Remember, these were all well below TC. Now we're going just above TC. So TC is 2.3 degrees. We have 4 degrees, 3 degrees, 5 degrees. And what we see as we go up in field, we see the same kind of thing happening. We see this something is growing, something's deepening, something's splitting. That's also things are happening in 110, but I'm not going to go into that. So when we're below TC, or about twice times TC, okay, not higher than that, we see this thing growing with applied field, which I'll show you is linear. And just to show you some nice data, if we go above twice TC, so these two plots are taken at 10 degrees and 15 degrees. TC is 2.3. The other three plots I showed you were 5 degrees or below. Now these are 10 degrees and 15 degrees. So we're, significantly, more than twice higher than TC. And what we see is very, very little change. Here's the background conductance, and we see a little bit of change, but we absolutely do not see that field splitting or whatever that is. So that only appears T below TC or T below 5 degree, about twice TC. So these are just plots, okay, to show you that the green is that splitting, okay, at the higher temperature and the lower temperature. These are all fits to show that we can map out the order parameter. So this is just really to show that, I'm sorry, I said the wrong thing. This is the peak to peak to position of that splitting. And the black is what you call steepest slope. So when you want to figure out if you can't really fit what the gap is, instead of doing peak to peak, sometimes you'll just take the steepest slope. But basically it's linear. The magnitude isn't important, but we do have this linear splitting that goes all the way up to 18 Tesla that we've measured. You saw this, and I remember John Rao was my postdoc advisor, and single impurity condo scattering, if they have measured this, there's no superconductivity in this picture. What this is NIN tunneling with some magnetic impurities in the barrier. And just to remind you that what was shown, and it's been a popular area and it's been revised again, is that you can certainly get a condo peak in the center, but what's important is this condo scattering does give you a linear splitting. It does split linearly with applied field because it is a Zeeman splitting. This is stuff, if you don't know it, it's really fun and worth reading when you could actually get through a paper and they explain things for you. And this is some statements on the Landé G factor. It's approximately 2. This is just showing that this theory here was the Anderson-Applebaum theory, and I don't think it's any big deal to tell you that we can fit the data, BTK, and we can fit Anderson-Applebaum that's linear splitting. There's a lot of parameters in there. I'm not sure we can know. So this is sort of what we're guessing here, and it probably isn't right, because when I showed you that condo scattering in the barrier and the linear splitting with applied field, that's looking at a single impurity condo in the barrier. To take it to this level has to do with me reading this paper by Rebecca Flint and Piers Coleman, and the other one with Maxim DeZero, which I've read many, many times, and I still need it explained to me. But the bottom line is, getting very heuristic here, is that there's a Kramer's doublet at the F level. And I have to put everything in my terms because I'm not good at computation. The F level, there's Kramer's doublet, so you're allowing 2 separate electrons to scatter off of that single F level. And that scattering of those 2 separate electrons after that doubly degenerate F level, if you apply a field, it will, if you split the Kramer's doublet, it'll split linearly with field. So the idea is that as long as you have any pairing at all, you're going to get that linear splitting. If you do this at higher temperature, when you don't have those correlations, then you're not going to see a linear splitting. So this is an argument where we see something below TC and maybe something above TC that carries that. I'd love to talk about this more. I want to show you, this is a noise measurement that we set up to do. We did it on lead. That shot noise is supposed to tell you if you have preformed pairs or not. if anybody wants to take over this experiment, I try to get Doug to do it. We have the setup. But I want to bring up this thing. So Tucson Park published this recently with Xin Lu, was my old PhD student. It's a nice argument. We don't cover I don't know why they didn't go into the same temperature and field areas. They could have done that. But they did show in their area in above TC doing pressure dependent point contact spectroscopy that things fit very well as one would expect. There's hybridization. Okay. So this is why we do this, but basically I want to point out that just like the cuprates, we have a pseudogap region, and within the pseudogap, just like the cuprates have an area of preformed pairs with the Nernst effect and stuff like that, we think we have that in serum cobalt-5. Why shouldn't it be a rich pseudogap structure? And I will be happy to take questions now. Thank you. And Irfan, if you want to
I
wave
wasn't.
to anyone, put your camera on, that would be great.
Yeah. Thanks so much, Laura, for a really nice talk. Any questions, comments
Let
for
me ask a
Laura?
question
Yeah,
to Laura.
Benjamin.
Yeah. I mean, I really enjoyed your talk each time, even though I heard it more than once. Yeah, this is the second time I heard it. So one question I have is that you mentioned about this, lead. You actually seen the sort of the ripples in the tunneling spectra, but it's also known that the serum, indium cobalt 5 has a very strong resonance, right? So I mean, I haven't seen in your data you actually have that. Do you know why?
Oh, that's a very good point. Thank you for asking that. So we know in the cuprates and in the iron-based superconductor, there's the 1 over 40 or the 40 millielectron volt inelastic neutron peak, right?
Yeah, it's been
That
seen.
is seen in the tunneling. That helped
Right.
identify that spin-spin correlations played a major role in the pairing mechanism. We
Right.
just don't have that, right? So I hate to talk about so here's the figure, the page for you. As you know, there have been neutron resonance seen in serum ytterbium, cobalt-5, ytterbium, right? But we don't see that in the tunneling,
I
right?
see. Do you understand why?
It probably isn't playing a role in the pairing mechanism.
I see.
So that's the people were telling me, Laura, it's D wave. It's got to be dx squared. It's got to be spin-spin correlation. And my argument is pairing symmetry doesn't give you mechanism. So the other thing that I like to point out, as long as you're paying attention, thank you, pinching, is that the iron-based superconductors and the cuprates don't have F levels.
That's true.
Yeah. So why should they be the same thing? So if we don't wear, when I was talking about D wave in the early days, people thought I was crazy, but that's because they understand superconductivity so well. So if you step back and say, I don't understand this, what could be pairing? And you see this thing that has a Zeeman splitting up to twice, something's going on there, and it's not just spin-spin. Yes, you have hybridization, but it seems like we also have something else going on that only goes up to twice TC and splits linearly with applied field, which screams Zeeman to me. So anybody else that wants to help me figure this out, and Irfan Mohammed, who's on here, we'd love to discuss this further with you.
Yeah, thank you, Laura. I thought Jeff had a question. Yeah.
No, I didn't have a question. I was thinking about the resonance, but I realized that the data don't show that. I just applauded.
That's
Nice.
what I said here. Yeah, this thing here, and the cuprates, the
Yeah.
inelastic neutron resonance, which you guys know much better than I do, it's absorbed. It's observed.
Yeah.
So the electrons feel it when they tunnel across. And so,
yeah.
Okay. Anybody else has questions, comments for Laura? Maybe I can ask a question, Laura. So I see two phenomena that you emphasize. I'm just wondering whether they, from your perspective, whether they are the same thing or in principle they can be two. So one is the response to the magnetic field, which magnetic field seems to dig a gap, and that seems to go along with the condo, some kind of condo effect.
Well,
That's
some kind of
possible.
Zeeman split.
Some
Not
kind of
kind of
Zeeman-induced digging of the gap in the spectrum. And the other is that it persists, or whatever the feature we're talking about, as you raise the temperature, even at the zero field, these features persist to higher temperature, to twice of TC.
This is really a mess. I'm sorry. These things are really hard. So if you just look at temperature dependence, you know you have something above
Right.
TC. That's only the temperature dependence. Now,
Right.
if we go to low temperature and look at the field dependence, that's when we get this splitting. I don't know if it's a gap increasing or just a splitting.
Right.
But so these are distinct. So we know we have something that lasts above TC, about twice TC. Yeah, maybe that'll help. If this is TC, if this is one, this is, this is about twice TC, right? If this is TC, this is about twice TC. It's not exactly, but that's pretty much what we see, is that something's going on about twice TC. And so we can see this magnetic field dependence when we're below TC or up to twice TC, approximately twice TC.
So, but I'm just wondering whether I could think it in the following way, that in terms of response to the magnetic field, the data, I would say, provides very compelling evidence for some sort of local moments that's underlying the low energy states.
That's all I'm saying. And
And
I've come up with better explanations, and I don't think
this
I don't know if
is
they're right.
beautiful to see. But in principle, whether this feature persists above TC or not, could it be something? I mean, I'm sure in the end it's related in some way, but in principle, it's a different feature. Would you agree with that, or do you think they are tied together?
I like to argue that they're tied together.
Hmm.
And the only reason I like to argue they're tied together, and let's go back to this one, um, or that one grows out of the other, maybe, I don't know. But just from an experiment, we have a lot of data on these things. And the fact that it smoothly goes, nothing is sharp. And when we're down here, even here we're below HC2, and we clearly have a little bit of structure that there's superconductivity due to the coherence peaks. But this thing is already growing. So whether they're related or not, they seem to exist simultaneously. As the superconductivity goes away, this increases.
So from that perspective, just to follow up on this, would it be fair to say that the picture you are inferring from the data is that there are underlying local moments there are local moments that underlie these excitations that are being probed, and
That's our,
presumably that feature is also making some sort of continuation of the superconductivity, superconducting like excitations above TC, some kind of a pseudo gap.
I think that's a good way to put it. What we're saying is that this the doubly degenerate F levels allowing two electrons to scatter off of it, which Pierce says is an Andreev reflection, which I still
Yeah.
don't get. But that gives you some coherence. If you have pairs above TC, which now is not a surprise anymore. 30 years ago, that was not believable. But now we do see pairs above TC that are not condensed. And so if you argue there's still some pairing due to this coherence, but even though it's not condensed, there's still some coherence between pairs that haven't condensed in a single state. And that's what we're measuring.
Okay, great.
Did that make any sense?
No, this makes a lot of sense to me. Yeah.
Okay.
Thanks so much. We still have a minute. Any further questions?
I was just curious, Laura. I mean, are there any other signatures? I mean, of this a feature, roughly twice TC
Good
from
question.
transport or NMR? Anything else?
Certainly transport, to the resistivity versus temperature, you see
I see. A broad peak.
And I can't remember, we looked up the NMR. Irfan, if you remember this, cut in. And we want to look at the shot noise.
I see.
So
But the magnetic susceptibility might be informative to look at the temperature.
yeah, it might be. Yeah. I have to go look in the literature again. I should be more prepared for this, but yes.
Good question.
So
All
these,
right.
I'm going to remember these questions. I'm going to look at them again and get back to you.
Thank you, Laura.